Hi everyone. So today I'm going to tell you about a new backend for the Manticore compiler based on LLVM. Okay. As some of you may know, developing and maintaining a code generator is kind of a big hassle, and LLVM has emerged as this default backend that most compiler writers will reach for when they need native code generation. And in particular these days, a lot of hardware is becoming more specialized and having instructions that often there's like new instructions that your backend you might want to take advantage of with each new iteration. In addition, LLVM is actively developed by both industry and also used in research. Apple is a major sponsor of the development, and there's also a large community of volunteers that contribute and maintain the compiler. And in terms of research, there's a lot of fun research projects that work with LLVM, such as LLVM IR Super Optimizer. So there's a lot of neat stuff you can do with LLVM. So a bit about the LLVM, or how LLVM works and how it may fit into your compiler. At its core, LLVM is the LLVM IR, which is the language shown in the blue box, and there's just an optimizer and a compiler, or at least these are the core parts of LLVM that are really a concern for code generation. LLVM has really grown into this large umbrella project that in many ways includes Clang, which is the C++ family compiler, but this is the overall structure, and I should probably now have maybe WebAssembly on the right side for the backends you could target. And so in today's talk, I'm going to focus on this red arrow here, which is how we compile parallel ML programs using LLVM IR, and it's integrated into the Manticore compiler. But there's also already some compilers that are functional languages, but our compiler is a bit unusual. Okay, so first, I also want to just talk briefly about LLVM IR because I have some examples in it. LLVM IR is in a canonical form called static single assignment. This, as the name suggests, you can only assign to variables once. We have these phi functions here which maintain the illusion of single assignment because they merge variables of different versions along different control flow paths in this basic block. So functions are basic blocks, and they're denoted by these labels here. So one thing to kind of realize is that LLVM IR is kind of seen as a portable assembly language, but the language actually kind of resembles C, but kind of single assignment C. In particular, there's no control over where this variable n is going to be allocated, and it assumes that you're going to use a C stack for the return continuation on this non-tail call to factorial. I mean, it's kind of like assembly with types, but with some C flavor. Okay, so now Manticore's runtime model is quite different from C. We use first-class continuations for a ton of things. We use it for parallelism, we use it for exceptions, we even have software transactional memory implemented with first-class continuations, and we use CPS in our compiler, and thus we have continuations which are explicitly passed to functions, and we also heap allocate our continuations, which is something that's a little trickier to do in LLVM. Obviously, we never use LLVM's returns. We overturn by just throwing to another exception, so our functions tail call and they never return. So this is the basic structure of the LLVM compiler. We have a direct style IR called BOM, where we do some optimizations, and then we do CPS conversion to our CPS IR, and then we also do closure conversion. And in CFG IR, we basically have the program in a first order continuation passing style representation, and this is the part where we have this kind of mismatch where we have this continuation passing style IR, and then we need to get to LLVM. And that's really what I'll be telling you about, and in particular, the challenges that we faced when developing the backend to produce LLVM IR. So these are really the main kind of sticking points that a lot of front ends that are functional have when they're targeting LLVM. And in particular, they really need efficient, reliable tail calls, especially for us since we're CPS. They need garbage collection, and especially for Manticore, we need preemptive scheduling and multithreading, which is becoming more common these days in a lot of language implementations, and we use first-class continuations. So this is basically going to be the structure of my talk, and I'll be telling you about how we solve these problems, and I also have an evaluation. Okay, so what's wrong with tail calls in LLVM? Well, a bunch of things. The tail call optimizations have some bugs that have been hanging around for quite some time, like probably years. Some of the more experienced developers have even reported some of these bugs. One of the developers that's quite experienced actually said that they tried to fix it, but they got into a fight with the instruction selector in LLVM. So that's kind of difficult. That's a bit of a challenge for us, but luckily LLVM has at least correct tail calls in that the stack is cleaned up when you do your tail call, because since we're CPS, we can never clean that up ourselves because we never return. So that's a major problem. But also efficiency is really a concern for us as well, because every single function call is a tail call, and we encode all of our loops and everything with tail calls. So any overhead here is going to impact us, both in terms of code size and execution time. Okay, so before I tell you about how we solved it, we need to dig a little bit deeper into how C-stacks work. I apologize for kind of throwing some x86 assembly at you, but this is the only way I can really explain it. So, the figure on the right is what the stack looks like immediately after this non-tail call to bar. So this is an example of a non-tail call in C. And so the return address is pushed here. I've just marked it with after. And so this is what the stack would look like once it's all set up by this prologue. And so the prologue has a couple components. One of them is these pushes, which are really saving callce saved registers to the stack. And then we have this sub here, which is can serve two purposes. One of them is doing stack realignment, because many system ABIs require the stack to be aligned in order to call C functions. And also it's for other temporary register spills that the function may have, especially in the body of bar. And similarly, the epilogue cleans up this stack. So this is exactly the same sequence of instructions where I've bumped the stack pointer down and I've bumped it back up to clean up the stack. And then I do a return, which pops the return address off the stack and then jumps to it. Okay. So, now what if foo were made a tail call to bar instead of doing a non-tail call? Well, that would mean that there's no body of the foo right after this call, and all we have here is this epilogue. So what LLVM's tail call optimization, at least the guaranteed one, tends to always produce code that looks like this. And this is rather kind of silly because we push all this stuff on the stack, we execute bar, and then we just pop all of this off. And it seems as though this is rather inefficient, especially because we're in CPS, where we know we don't have any registers that are callce saved because we don't return. And it's kind of silly to keep setting up the stack and then bumping the stack down for spills and then bumping it back up on every call. And so really our goal is to have code that looks just like this. All we need is a jump, specifically a jump with arguments. That's what we need when we're doing CPS. So what do other backends do to get around this? Well, Milton's backend for LLVM uses a trampoline, which is basically just getting around the whole tail call thing, so they don't emit them. And in particular, they do this because this is what they would do when targeting C. GHC's calling convention gets rid of the callce save instruction overhead, but they don't get rid of the stack creation and then destruction for spills and also for stack alignments. We're able to remove all the overhead and get just a jump by using a calling convention that also has the no callce save thing, but also we use naked functions. So naked functions in LLVM are kind of a bit dangerous, and they were really originally designed for interrupt service routines, or to support them for hardcore C hackers. So this is a really undocumented or poorly documented feature in LLVM. There's really only like one sentence in the LLVM documentation. It just says, very system-specific consequences. If we use it carefully, we can use it successfully, and that's what we use. So the basic idea, by the way, for naked functions, we mark every function as naked because we don't need a frame, and we will handle setting up the frame ourselves. So that's what we do. In order to use naked functions, the runtime system sets up the frame, and it sets it up once. And the idea is we set up one large reusable spill area that can cover basically every function that is needed, that needs stack space for temporary register spills. And in order to be safe, because this is hard-coded, handwritten assembly code that sets up this frame, we use the compiler to limit the number of spills in every function. This is an idea borrowed from Standard Model New Jersey, and it's also described in Appel's book on how to do this for safety. And in practice, we just set this size to be quite huge, so we never have to worry about it. Okay, so as I've already mentioned, that every function will use the same frame, and I've marked this boundary here because we just, in our assembly code, we just make sure we abide by the system ABI manually by making sure we have the right stack alignment. And that's why I have this here. Stack pointer should be right before the boundary so that we are able to make foreign function calls with 0 overhead. So. All right, yes.
Do you have to make an alignment if you're not making a cycle? If you're unnecessarily making stack alignment?
No, we just do the stack alignment once, and then every time we do an FFI call, because when we make the call, the C ABI dictates that the caller has to then, or the callee has to put the stack back in the place it was originally. It always stays aligned. So once it starts aligned, naked functions never touch the stack pointer, so it's always aligned. Okay. So yeah, we can't use LLVM's GC support because it assumes we use a stack, but we don't. If you'd like to know more about how LLVM's GC works, if you do use a stack, you can talk to me afterwards. I know quite a bit about how that works. Okay, because it's rather recent developments. Okay, so as I've mentioned, the stack frame is only used for temporary register spills because everything that's live is only in the registers when we do a jump. So actually GC for us was quite easy because we don't have to parse LLVM stacks. And, but the only thing we have to do is we have to insert heap exhaustion checks before we do LLVM code generation. Okay, so I have an example of what this looks like. Basically, we have this invoke GC function which we keep external and away from LLVM looking at it. And the idea is we save all the live values in the heap as just a normal allocation, and then when we pass all of the roots and the allocation pointer to the GC function, LLVM must use all the fresh values that are returned from the GC. And then we just extract them, and then we go. So our heap check is very simple, it's just one branch, and that's it. And we obviously just merge all the updated values. And it's basically how, that's basically all we have to do. We didn't actually have to modify our garbage collector at all otherwise, once we did these heap checks. Okay. So Manticore is has a parallel runtime system, and we need preemptive scheduling, and so continuations are a very nice representation for suspended threads. In particular, when we do a preemption, you can kind of think of this as continuation capture. So, but the downside is when you do preemption, you can't just preempt the program at any point, especially in a precisely a language implementation that uses precise GC, because if you're in the middle of an allocation, you can't just stop the program there because you might have some weird derived pointer or your allocation might not be done. So actually safe preemption is a bit tricky with this kind of runtime system. But we also use another idea that's used in Standard Model New Jersey, which is to do preemption at safe points, specifically garbage collection safe points. So the basic idea is we use heap tests, and we can have other threads make the heap test fail in order to have preemption. So the idea is threads keep their heap limit pointer in shared memory. Other threads can access it. And yeah, we just force the thread's heap test to fail. You just write 0, and then you tell the thread to, hey, enter the GC at the next point you see a safe point. And yeah, we have our threads enter the runtime system via callce, or at least the runtime system will do that. And so non-allocating loops are also given a heap test. This is in order to not get stuck in a loop and actually respond reasonably to signals. And so this is kind of the pseudocode that we're doing here now. So our GC tests really need to be able to do this.
How do you know what's in?
We use, I think, a feedback algorithm that can find the cycles in the control flow graph, and then we just put a node that has the heap test there. So we can identify the loops, and we just put the allocation checks everywhere. So yeah, these heap checks are all over the place then. They're in every loop. Okay. So this kind of gets to the really kind of trickier part, which is preemptions need to be able to happen in the middle of a function, and these preemptions with callce's don't correspond to the explicit continuations that are in our normal representation, in the program representation. These are like kind of implicit. So the difficult part is that in order to create the continuation closure, we need a place to jump back to, and LLVM does not have first-class labels. And so this was kind of the barrier that we ran into for a while in LLVM. And also first-class label support in LLVM is not something that you can really expect, because it kind of violates some assumptions about how SSA works, because you have an edge from an unknown caller coming into the middle of a function. Okay. So a couple observations about how we can get around this problem. The return address of a non-tail call is a label that's generated at runtime. Okay? And LLVM allows us to specify any calling convention we want, and in particular for structs. We can have our own calling convention. And when I'm talking about calling conventions, I mean that the locations of the arguments and where they're passed, either stack, register, and which registers in particular. So our trick is we treat the return address like a first-class label, and we get LLVM to generate code that follows the non-tail call that matches the same calling convention as we would have if we were to do a normal tail call to that location in the code. So let me make this a little more clear. So this is the full calling convention we have with jump with arguments. Argument 1 is passed in the same register that field 1 would be passed in if the C struct that's returned in that field is passed in that register. Sorry. The fields of the structs match up with the arguments that would be passed if this were a call, but this is a return. And they use the same locations, and in this way we can basically tail call our return addresses safely. So let me walk you through an example. So here we have this gen label, which this is kind of an example that's similar to our GC check, but in particular I'm trying to allocate a closure, but I have this undef for the code pointer because I don't have first-class labels. And the idea is I pass this closure pointer that's not exactly finished being allocated, and I also pass the location I want to end up in. And then gen label, after compilation, gen label here has a call, and this is an assembly instruction which pushes the return address onto the stack, and LLVM is now told that what the calling convention or the return convention is after that for that return address. And so all of the code following that call uses the same convention. These registers have these values. And so what we do is we immediately, in this handwritten assembly, pop the return address off the stack, and then we put it into the closure. In this way, the function can be tail called directly and safely, and there's no other overhead. We just have this one pop instruction after the call. So we're basically abusing non-tail calls in order to get first-class labels in order to do callce in this way. So a bit of a hack, but it works just fine. Okay, cool. All right, so let's talk a bit about numbers, because this is a more empirical kind of thing. In our performance comparison, we wanted to get an idea of how the LLVM code generator works, or LLVM backend works compared to our old backend, which is based on MLRisk. So these numbers are normalized, and these are execution time speedups. At the top here, I have basically all the different groups of passes that we apply to the code before we give it to LLVM's compiler. So these are the optimization passes we use. What I have in quotes are basically groups of passes that I handpicked the ordering and the passes that I thought were actually profitable, but these are also the default ones that the optimizer has. So you'll notice the end body is quite a high speed up, and the reason for this is because MLRisk does not have any peephole optimizations for floating point arithmetic in x86-64. So we just blow up here because the code generated by MLRisk is a lot longer because we don't have those peephole optimizations. And you may also notice that the Takeuchi benchmark, which is really just a recursion benchmark that tests the overhead of recursion, for some reason some of these optimizations are down by like over 10%. And I found out the reason for this. It's because there's a memory operation vectorization pass that LLVM does, and it makes a kind of a poor decision to vectorize the allocation of a closure in the middle of a hot loop, because those vector instructions are more expensive to execute than normal move instructions. But otherwise, the LLVM backend gives us a nice little boost here and there. Obviously, quicksort doesn't get any help. So, yeah. So I guess to conclude, we hope to be able to apply these ideas in Center Melville, New Jersey in the future, and I hope to upstream the jump with arguments calling convention so other people can use it. And I also plan to put out a tech report with some other kind of war stories about how to target LLVM. In particular, it's a bit tricky to generate textual IR that's actually correct in LLVM and to get everything to work right. So I was going to put a little bit there. So thank you.
We have time for questions.
I think that having an LLVM backend is useful for other things that performance. But that said, it's a lot of fun for 10% improvement. And I think you could find better benchmarks that people care about more than Takeuchi, for example, in which you have better results. Because, for example, numerical code as the endbody, people want to make it fast and LLVM is good at it. So maybe you should go looking for better benchmarks to do what you
Yeah, so I picked Takeuchi. I know like it's kind of a, like there's like the no-fib benchmarks as well in GHC, and I guess the name comes from that's like a bad example of benchmark. But in particular, the challenge we had is getting really efficient tail calls. And I wanted to be able to compare it with our old backend, which has very efficient tail calls. So I felt like we really needed to include it in this case. But I agree that this is really more of a preliminary evaluation that I ran with this backend. So we're still, yeah, working that out.
There's time for more questions.
So, by switching to CPS, the code that LLVM sees is very non-idiomatic, right? It's not anything like LLVM would usually see as the part of C program. So that kind of hobbles all the, the optimizations that LLVM is working really hard to do things that really you've already done if they're going to get done at all. Is that right? So, if you can somehow generate more idiomatic LLVM some of the time, I can see why you don't, and we don't either. But
yeah,
it's always a bit tantalizing that somehow we're putting the program in a form in which LLVM basically has no chance, except for doing people optimizations at floating point, obviously.
Exactly. Yeah, so many of the optimization passes LLVM has are for loop analysis and loop optimization, but many of our loops are tail call loops. That's why I actually handpicked some optimizations that I thought really just clean up the code, because I felt we don't really need to waste any time running. Like O3 doesn't really get us very much. Just clean up the code so that it actually looks like it was generated by Clang, because that's the one that the developers are really focusing on. Make sure when code generated by Clang comes out nice and clean. But otherwise, yeah, LLVM is really, our expectation is to use as a code generator, not really an optimizer. Maybe using the super optimizer might be fun or something.
For example, maybe the simple tail recursive loops. Maybe you could really generate a loop that looks to LLVM like a loop.
Yeah, so we could do tail recursion elimination, and I did experiment with this, but it turned out to add a little bit more overhead than you'd expect. In particular, there's kind of a mishmash between C calls, which have their own calling convention, their registers, and what our calling convention, the registers we choose were. So tail recursion elimination sometimes helps, but otherwise just kind of messes things up. So it's still tuning it a little bit to get a little bit more performance, but I think optimizations are better done earlier in the stage, especially because this is the CFG representation is rather low level already. So.
No, Darren?
So I did something very, very similar to this a few years ago with also doing the jump with arguments, like all the convention using that to do context switching. One thing that you can do when you have that, which I'm wondering if you've planned, is not using CPS, using Heap calls, right? Like using like a real stack and normal C function calls, but using that sort of jump with arguments type stuff to implement one-shot callce to allow switching back to other threads.
That is something I have considered, but that's still kind of a work in progress, I guess. So, but yeah, definitely.
Okay, thank you again.
Yep.